So I had a couple of things I wanted you to work on, and I'm going to very quickly demonstrate how we can do one of these. So, first question. First question here, I asked you to do the MD1Q numbers. The MD1Q numbers. I don't need to do the math. You're very smart guys. You're very brilliant. I can just look at these formulas here. I can just look at the formulas and tell you what I expect the numbers to be. So for, oh, here we go. I have the numbers up here still. So for MM1, the length of the system was 2. The length of the Q was 1 1/3. Here's our formulas for MM1 here. What should those values be for MD1? What should those values be for MD1? Sorry? Sorry? Which direction are they double? Which one is double of the other? Which direction do things change? We did MM1 before the break. I asked you during the break to do MD1. What's the difference? What changes? Stefano.
The LQ of MD1 is half.
Yeah. Yeah. So look at the formulas on your page here. L of Q, M1Q system. L of Q, MD1Q system. What's the difference? The number 2 right here. The length of the Q in this MD1Q is half the length, on average, of the MM1Q. What's the difference between those two Qs in their behavior? What makes them different? What makes them different?
The second one is more predicted.
Yeah. Yeah. The second one, in what way? You're right. I mean, I want to walk that conversation. What does that mean? What is different?
Because the service is determined.
Yes. Yes. So in the MD1Q, we have removed the variance from the service time. This service time has variance. It's variable. It's a Poisson distribution. It has a random service pattern. This system has no variance. We didn't add more servers. We didn't change the number of customers. We didn't change the structure of the queue. We cut the variance. We eliminated the variance in the service process. And that one step improved our service performance. I guess depending on how you want to phrase it, it doubled our service performance, or it reduced our waste by half. Length in the queue is cut by half. I'm sorry, count is cut by half. The inventory in the queue is cut by half. And of course, our time in the queue is cut by half because by Little's law, the rate of the flow has stayed the same, so we cut time, we cut inventory, and vice versa, cut inventory, cut time. All by reducing the variance. So, this explains why so much time and attention is given in business conversations about lean management, Six Sigma, total quality management, all these things where we're talking about cutting the variance. How do we cut the variance in our processes? How do we train employees to do things very predictably without any variation? Why do employees follow scripts? Scripts when they're doing either customer service interaction or they're doing things like checking the fluid levels in a locomotive. Get rid of the variance. Make sure things are predictable, they function exactly on time, get rid of the variance. That is a huge driver of efficiency in this system. We can't control the customer, very often. It's very difficult to control the customer. We can try to influence them with pricing and market promotions and reservations and things like this. It's still difficult because the customer does what the customer wants to do. But we do control our service. We do control what we deliver. And so cutting the variance is a major, major way of improving our efficiency. From a railway management point of view, from a railway system, we want to improve the efficiency of our trains, our track system, our track blocks. So we want to cut the variance of how our trains consume track time so that the trains will more efficiently use the track blocks. Now, to give you the quick answer, you should have for your spreadsheet, I'm going to do a quick spreadsheet demo here. So we have lambda equals 3 per hour. I'm going to zoom in on this so you have a better view. Come on. Zoom in here so we got a better view of what I'm doing. Good. So 3 per hour, and then I want to have different levels of utilization. So I'm going to go from 5% to 95%. And so that means mu is going to be and I'm going to name this cell oops. And now, just for fun, let's do length of queue. I've got this backwards. I've got this backwards. I want this to be 2, and I want this to be, I've got this backwards. 2, and I want, I've got it backwards. I want this to be mu, and I want this to be lambda. Sorry about that, leading a wild goose chase. There we go. That's better. Now this guy. There we go. Sorry about that. Got my head tangled in the opposite direction. So mu, from the previous example in the slides, we had a service rate of 3 per hour, just for argument's sake. And these are our utilization targets. This is lambda divided by mu. So at a service rate of 3 per hour, then 5% utilization is 15.15 per hour. And then I've got the length of the queue over there on the right for MM1. And then I'm going to do the length of the queue for MD1, and of course it's going to be just half of what I just did. So oh, here we go. And then, of course, then insert a graph. And so you can see it's not the prettiest graph, but you get the idea. Cutting the variance out of the MD1Q is dramatically cutting our service time, especially as we get into a higher level of utilization. This is 5%, 10%, 15%, chick, all the way down here, and then this is 80, 90% right here, and suddenly we've got a bigger and bigger gap. So cutting that variance is a big deal in improving the efficiency of the system. So why does this relate to what we're doing in railways? Well, now we have a queuing system. This block is a resource. This is a resource. This is a resource. They have a service time. They have a service rate. These blocks can process so many trains per hour. And depending on how the network is managed, this queuing system might be closer to MD1 or it might be closer to MM1. Depends on a lot of things. Depends on how well these trains are equipped to get across the line efficiently. If we're looking at North American freight traffic, these are a lot of variation, a lot of random variation, because the trains are not powered consistently, they're not braked consistently, they have all kinds of stuff interfering with their getting across the line. If this is the Copenhagen Metro, it's really tight. I mean, there's not a lot of, other than, you know, some kind of other external interference within the block itself, there's not a lot going on. It's computer controlled, the trains are driven by computer, there's not a lot of stuff going on, so it's much less variance. So that's what we're doing here. And so we can use queuing theory, we can use simulation products to simulate the movement of trains. There are many dedicated products specifically just for simulating dispatch of railway lines. We will probably see some of that at the end of the semester. We have the queuing priority here. This is a single track line, so it has to be first come, first served, but suddenly you add sidings, you add some places for trains to overtake, and now you might have different queuing disciplines to worry about in the operation of the system. And again, we're worried about managing the random variation. Whatever we can do to cut down on random variation will improve the operation of this queue, will improve the operation of this system. As I demonstrated here, though, sometimes that random variation is not, quote, random in the sense that it's totally a surprise. It's random in the sense that decisions beyond our control create the pattern that looks random or that behaves with a random pattern. So, for example, we could have a series of trains that are of different types, passenger, freight, regional, S-tow, whatever. And because we sequence those trains in a heterogeneous pattern, in a mixed pattern, we could end up with kind of, quote, a random behavior, even though the whole thing's running to a schedule. Even though we planned it that way, it's going to mimic the behavior of a random system because of the natural variation that we are putting into the system by mixing different train types together. So even when we think we're running a scheduled railway, we still may be forced to treat systems with many of the characteristics of a random process, of a random queue, because we have introduced that mixture, that variation in the system. So we're repeating things I've just said here, and there are many papers I've seen that apply queuing theory to managing train marshalling in yards or to managing flow across the railway line and that kind of thing. Much of what we've just learned, as we've seen, has a lot of strong assumptions about how it behaves. Strong assumptions that the population is a certain way. Strong assumptions that the distribution probability is a certain way. Strong assumptions about the queuing discipline that we're going to apply. And as we mentioned a little bit ago, there's a bit of a problem in that we may find lots of situations in the real world that do not follow those assumptions. And somewhat disappointingly, there are not nice, easy analytical equations like we just learned for the basic queues that will give us the answers for those systems. So when we have that problem, we then have to resort to numerical methods. We have to use software, we have to use numerical sampling to emulate, to mimic the behavior of some system that does not naturally follow the clear rules of a queuing system that we have already analytical equations for. So I want to demonstrate here in this mid part of the lecture fundamental theory behind simulation, some fundamental concerns in simulation that you should be aware of, particularly when you are a consumer of simulation products. One of the things that really concerns me is that there might be simulation tools and commercial applications out there that are in fact not theoretically correct. It really does concern me. And I can actually quote you, sometime over a drink, I can actually quote you a conversation where I actually contacted the publisher of a piece of simulation software and wanted them to reveal to me how they generated the numbers in their software, and they did not want to do that. They said it was a trade secret. And the problem was I needed to know what their trade secret was in order to defend the use of their software in my research paper. And that makes me nervous because it makes me concerned that maybe some of the people generating some of these software programs do not in fact have a training in, they might be great programmers, and they might be great computer geeks, but they are not actually trained in the theory of simulation, and they're not actually composing their programs correctly to do things numerically correct. So I want to present to you some of the key things that you should be concerned about in selecting simulation software, so that when you're in the position of either purchasing software or working with a team of programmers to develop some kind of a simulation package, you're at least a little bit aware of what you should be careful about in making sure that your results are numerically correct and defensible. So what we're talking about here is discrete event simulation. It's called discrete event because these guys are discrete events, right? We're talking about a discrete event. We're not talking about, as opposed to, there are simulation tools in a whole different industry that do things like simulate the flow of water, or simulate the filling of a dam, or simulate the operation of a nuclear power plant. These are not discrete processes. These are continuous processes. The water from the river flowing into the dam is not a discrete process. You can't stand there and say, oh, 1 gallon done, 2 gallons. It's not that way. It's like drip, drip, drip. It's a continuous flow of water that's continuously moving. So it's analog. It's real valued. We're looking at trains on pieces of track. These trains leave at specific times. They make movements and occupy specific pieces of track. The train itself is a discrete object. It is a train. It's not a collection of axles. It is a whole train. So these are discrete objects, whole integer objects. So we are interested in discrete event simulation. We want to simulate the discrete movement of whole objects and the exact complete movement of these things through decision processes, and trains are exactly like that. So we're doing discrete event simulation, and the most common kind of benchmark product for discrete event simulation in the commercial world is Rockwell Arena. There's another product called Simio that's kind of biting at its heels like a little puppy dog, but Rockwell Arena is the big gorilla on the block. Rockwell Arena is the big leader. Then Berkeley Traffic Controller, which I mentioned to you in a previous lecture, is in fact a discrete event simulation tool. It is only for trains. Rockwell Arena is a generic simulation package for anything you can dream up. Berkeley Traffic Controller and OpenTrack are only specifically simulation of railway trains on railway tracks. But they are all examples of discrete event simulation. So we want to talk about what this really is, how all of these products function underneath the hood. What do they really do in their engine? Well, they all have something in common. They all have a simulation clock. That is, they have, quote, simulated time. So they're running a clock and they're generating these kind of hypothetical fictitious times. And they have an event calendar. They're logging the events as they occur in a calendar. They're saying this event happened. This train entered this block at a certain time. We're going to log that in the calendar. This signal turned to red. We're going to log that in the calendar. This train stopped at a station. We're going to log that in the calendar. All these events are discrete events, and they're all logged in the calendar. And then usually the software has some kind of database that tabulates these events and can generate data such as how long did the train stop in the station? How long did the train spend on that piece of track? How long did the train stop at that siding? All of this tabulated by looking through the event calendar and tabulating the results, the output data from that event calendar. And then we have an event log. Actually, I've got these backwards. Event log is the output, is what we're tabulating from. Event calendar is events that have not yet been processed by the simulator, but are going to be processed. And we're going to see what I mean by that just here in a minute. So we have events being formulated by the calendar, and sometimes these events create other events. So for example, train stops at a station, and it occupies the platform at the station, and this creates events in the calendar that need to be processed in the future. It may create an event in the calendar that says this train will leave this platform at some time in the future. We're going to put that in. Oh, this train is going to need a signal set for it in the future. That's an event in the calendar in the future. The event calendar will queue those events up to be processed by the main simulation loop, the main simulation engine. And then after the events have passed, there'll be an event log that records them as history, that records them as have actually happened. So let me walk you through some of this. Here is a spreadsheet. I've handed this template out to you. We're going to work this. Let me pull up this sheet. Here we go. So this is a template for us to manually walk ourselves through what a real discrete event simulation program might do for a very simple example. So this is a manual simulation of an MD1Q. So we're going to have a fixed service time of 3 time units. Not 3 per hour, but the actual time of the service itself will be 3. And we're going to have a random arrival flow, and we're going to simulate that random arrival. We're going to use some kind of random number generator, a pair of dice, or in this case, computer simulation software that's going to generate a random number, and tell us what the time will be in between each arrival. So this is, in this case, it's an MD1Q. So actually here we're going to use, this number pool I pulled here is a uniform. So these are actually uniform arrival samples right here. So this is the random number table that we're using to generate our numbers to run this queue. So we're going to start with a clock start time of 0. And our first arrival is going to be at time 0. So I'm going to shift that screen over a little bit so you can see that, because I can see it's clipping the edge. I'm going to just make this a little bit smaller and scoot this over a little bit, because it's just, there we go, that's better. It's just clipping the edge of the screen right there. So we're going to initialize this. We're going to initialize this queuing system. And we're going to initialize this system. Entity 1 has already arrived. This is the initialization row. Entity 1 has arrived. It's going to arrive at clock time 0. And we're going to start actually logging its arrival into the system. So entity 1, arrive, clock time 0. And what we need to do now is figure out, and this is discrete event simulation software. So what the software is doing is it's saying, OK, the entity has arrived, the customer or the train, the entity has arrived in the system. And as it calculates the arrival of that entity, the very next thing it does in the clock is perform the calculation to determine when the next, it's actually going to queue up the next arrival to the system to actually start recording that in the calendar. So we're going to pull a random number from our random sample. And in this case, I've got them in order. So the first random number is going to be a 2. And that's random number 1. So we're going to use random number 1 there. And the next arrival is then going to be entity 2, and it's going to arrive at clock time 2. So this is the event calendar. These are things that are going to happen in the future. And so the computer software, the discrete simulation software, is maintaining this database of events that have to be processed in the future. So these are the events to be processed in the future. This is the log of what has actually happened. And this is where we're going to keep track of things that pile up in the queue. So the next departure is going to be this guy that just arrived. It's going to leave in 3 time units because it's got a fixed processing time. So the next departure is going to be entity 1. And it's going to leave at clock time 3. So this simulation product has just completed its first cycle of calculations on this table right here. It's initialized, it's processed the first arrival, it's filled the event calendar with future events, and it reaches that point in the programming loop where it pauses and then goes back to the top of the loop and starts over again. So now it's going to go back to the top of the loop, and the first thing it does is goes to the top of the loop and looks at the event calendar and says, what's the next event in the calendar to process? So which of these events is going to happen first? Well, this one's going to happen first. Clock time 2 is before clock time 3. So this event is processed next. So we process that event. Clock time 2. And we're going to, again, set up the next arrival. So as it's processing, logging this arrival into the discrete simulation, the program code immediately does the calculation to figure out what is the next arrival and put that in the event calendar before it goes any further. So it's going to put the next arrival in the event calendar. The next arrival in the event calendar is going to be entity 3, and it's going to come, we've got the second random number is a 4. So this one's arriving at time 2. The next one is 4 time units from now. So the next arrival is at time 6. The next departure is still this guy. We're going to copy this number down. We're going to copy that number down. And now we've got one in queue. We have an entity in queue. Entity 2 is in queue. It's the service is occupied by this guy right now. So we're going to put this guy in queue over here. And now we've finished that loop, and we're cycling back to the top of the loop and running the loop again. Now you can see we're just doing an MD1 queue with a real simple draw, and you can see we're already managing a lot of stuff. So you can imagine what a real commercial piece of software has to manage. It has a lot of data tables, but it's fundamentally the same thing that we're doing right here. Keeping a log of future events, sorting them by time, keeping a log of other things that are queued up behind active events, and then moving these things around in the data tables as we process through each step of the sequence. So we're back at the top of the loop again, and we look at this data table and say, what's next? Well, this is next. That's next. Naba. Well, it's just shorthand. This is where I reach the limits of a spreadsheet. And I'm going to want to keep a running log of what's in the queue. And this is just text shorthand. It's entity 2 at arrive time 2. And it's just my way of keeping track of who's in the queue. It's not meant to be perfect. It's just a demonstration. So the next event is the departure at time 3 of that first entity. So we put that into the log, into the event record. We're not going to pull a random number because this is a departure. So we don't, the departures, the services are fixed time intervals, so we're not drawing a random number for the service cycle. So there's no random number being drawn. We're just going to copy values down. And now we can push, this guy is gone. Entity 1 is gone. we can grab the next one out of our queue and slide it into the departure slot. So we now put entity 2 into the system. And it's going to leave. It arrived at time 2. It's a 3-unit time service, so it's going to depart at time 5. And then we look at this, and we're back up at the top of the loop again. We're back up at the top of the loop. We move this guy into the departure slot. This person has not arrived yet. We're looking at this row and saying what gets processed next. This is next. And so I'll just do one more row and then we'll quit, because I think you get the point. And next departure, we actually don't have a departure in there yet, because we have to process the arrival of the next guy. But we could work this whole thing out, and it would be, educational. We wouldn't ever want to do it again for real, because it's just too much grunting work. But this is what the real simulation software is doing. A couple of things that you can see straight from this picture right here that now we seem to need to be really careful about in management of the software. First thing, what's really driving this? This random number table is driving this. If these numbers change, clearly this changes. That is, if I were to resample this and give you a new table of random numbers, clearly my results over here would change. So this becomes a really important question about whether your software is doing things correctly or not. So there are two things you have to be concerned about in discrete event simulation software that are fundamental and, quite unfortunately, have not always been done correctly in commercial products. Number one, you need to know that it is generating random numbers that you can statistically defend as correct examples of the distribution you're looking for. Most simulation packages generate a uniform 0 to 1 random number and then interpolate or extract some other distribution by inverting that 0 to 1 number into the correct functional form of whatever distribution you're looking for. How that software generates that uniform 0 to 1 number can make or break the simulation. Now, things have advanced a lot since I was a wee little youngster studying this, and the power of the computers has grown tremendously. The literature on this subject is darn near mature, so the random number generators that you can Google and download off the internet, the code for them, the actual program code for them, is really good and robust and generates enormously well-defended random numbers. This was not true 20 years ago. And there are all kinds of tests you can run to determine whether the random numbers you're getting from some software package are defensibly truly random. Things like, are the numbers truly distributed in a nice even cloud? Or do the numbers have unusual kind of patterns in them that make it not really look quite as random as you thought it was? Are there problems where the numbers are not truly independent of each other? That could be a problem, where there's some kind of a cycling or sequencing in the random number stream that's generated. That's all advanced discrete simulation stuff, but it's very important that the software product you're using at least have somebody writing it who's aware that